And again, it's great to be virtually back. Unfortunately, I was hoping to come. I'm on sabbatical in Italy, actually, in the University of Trento for 1 quarter, and things are a little less calm. Like when I expected, I was expecting a little bit more like freedom to do things and go around, but unfortunately, a lot of things happen. So, but it's great to be back and see some of you from my old time at KTH. I was at KTH before joining UCI as a faculty some time ago. You see, I didn't have as many, gray hair actually. At this point, I'm a little more senior. But so today I'm going to summarize some of our recent work. I would say maybe like the last 2-3 years of our work on distributed inference for autonomous systems. And so a lot of this work actually started through a collaboration with the defense. Like here in the US, you see, we had a seed project with DARPA, the defense agency here. We built some of the system that you will see, and that led to more projects with National Science Foundation, so more fundamental research and industrial collaboration. Part of this work is funded by Intel Labs and by Cisco. We also partner with Verizon, IBM Labs, and RoboSense that are helping us in some of essentially collecting some data and also providing some additional funding essentially for some of the tasks that you will see. So of course, nothing of what I'm going to talk about today would happen without all my students. You see here some like my research group. And actually the main message here is that this kind of research, so I'm going to talk about reliable systems, reliable inference over distributed systems with wireless in between, is actually a problem that where you need a broad perspective. And you see that this is reflected in the group. So I have students who have a background in systems, students who have a background in machine learning, students who have a background in wireless and autonomous systems, students who are more like across different domains. And I think this perspective is very much needed actually to solve this kind of problem that is a composite problem of communication, computing, and application level reasoning. So, the kind of application that we want to talk about today are autonomous vehicles, autonomous drones, autonomous robots, smart manufacturing. And we have also another research direction, which is mostly focused on smart healthcare. And I'm just gonna briefly mention that project. Some of the solutions that we developed for autonomous vehicles and robotics also apply to some problems in essentially multi-layer systems for healthcare monitoring, for everyday setting monitoring. I'm just gonna briefly mention those, but of course I'm happy to talk later on, and please reach me out if you want to know more about that project. So what is the challenge here? So all these applications, right? So essentially to function, you need some form of decision making, and this decision making typically takes the form of extremely complex deep neural networks, right? So you can think of, for instance, an autonomous car, which is essentially executing models to analyze 2D imaging or 3D scans like lidar, and this is used to navigate, right, or to make decisions about where to go. And even these functions of a decision making may be a deep neural network, right? So we may have deep reinforcement learning, and even this kind of capable device, right? You think of a car, right, has limitations, right? If we do all of this in a car, the hardware will take the whole trunk, and actually a non-negligible portion of power and energy would go into the computing, right? So this is a challenge, which is also preventing this application from becoming like an actual reality. If you go down, right, one notch, and you look at lightweight drones, right, then the problem is similar. You still want to decide where to go. You still need to execute object detection, navigation control, and maybe other mission-specific sensor analysis and decision-making processes, right? And these devices have extreme limitations in terms of computing power, energy, memory, communication capabilities. So the problem of executing these kind of models is even more complex, right? And if you, our testing, I'll show you some examples. Even if you use relatively powerful embedded devices such as an NVIDIA Jetson Nano, you have to execute object detection continuously. Your energy consumption shifts from your power consumption shifts from 3 to 5 watts, and the whole drone, so a medium-sized drone, takes 24 watts to fly. So that's, the 2 watts more is almost is 10%, right, of the energy, and that's non-negligible, right? And again, with that only object detection, if you look at more complex reasoning, then you have more, of course, more issues in terms of all these aspects that I mentioned. So you can think of a system as like essentially executing this pipeline, right? So we are acquiring periodically, multiple times per second, 2D, 3D imaging. This actually corresponds to a stream of tasks, and every task essentially corresponds to the analysis of this kind of data, which are information-rich, complex data, right? And you want to execute object detection, image segmentation, depth analysis, planning. And the outcome of this actually feeds back to the drone to actually control the drone itself, right? And all of this needs to happen with some temporal constraint, right? Because this is all happening because we are trying to control the drone itself. So if you look at the like state-of-the-art models, right, for vision, for instance, and for instance, object detection. So one of the most modern detection model is the EfficientDet family. And so EfficientDet 7 has a very good performance in terms of object detection. So mean average precision has 55.1%. That again has a meaning in terms of accuracy of object detection, but has 52 million parameters. That means that you cannot even load the model on a medium-sized GPU, right? Like a Jetson Nano, for instance. If you go down to EfficientDet 0, which is the least powerful model in the family, you have 33% mean average precision, which is a drop in 20% from 55%. And this model has 3.9 million parameters, so you can actually execute it. But again, there are issues in doing this. If you go further down, so you take models that are actually designed to be supported in mobile devices like MobileNet V2, performance goes down another 13%. So you go to 20% mean average precision, and the number of parameters is 2.1 million parameters, right? So it's relatively simpler. The problem is that even this kind of small models can only run at like 6 frames per second on a Jetson Nano, and again, power consumption goes from 3 to 5 watts, which is a problem, right? So again, executing this kind of analysis in real time for drones for actually implementing like realizing autonomous applications, autonomous operations of drones is not an easy task. You can further compress the models, right? You can use pruning, quantization, knowledge distillation. That leads to further performance loss. That may be fine, depends on your application. But again, in difficult planning, having a degradation in object detection or essentially depth analysis or segmentation is a problem if you're navigating fast in a complex environment, for instance. Of course, we are all, well, obviously some of us are network researchers, right? So this kind of device is not operating in isolation, right? So you can think of this device as operating within a 5G infrastructure. So there are other resources that you can access. And an example is edge computing, right? So in edge computing, what would happen is that the drone would send the data to an external server, which is at the edge of a network, and the server would execute the task for the drone and send back the outcome. The problem, so this would solve some of the issues, right? So we are not constrained by the computing power of a drone. We are not constrained by memory, energy, reservoir of a drone. But the problem is that we have a wireless channel in between, and wireless channels are not typically nice entities, right? So we have a lot of variability in the system. You can think of this as, like a Wi-Fi to a high-capacity 5G link. In any case, you have variations in the capacity. You have also network load that varies over time. You have server load that varies over time. And all of this may actually induce variability in the system and in the performance of this distributed computing task. So that's a problem, right? If you have this task delay variations that may degrade control. And that's the problem. And so I'm going to show you just very briefly the system that we developed in our initial project with the defense. So we have essentially a fleet of drones, and we call it the Hydra testbed. We have larger drones, smaller drones, and rovers. They're all custom drones equipped with essentially a camera and lidar sensors, software-defined radios. We're now mounting multi-user MIMO radios, Wi-Fi interfaces, and embedded computers, right? So we can essentially create this kind of setting where the UAV is actually trying to compute locally on board, to, for instance, track an object, track a person, or is sending out the sensor feed to edge servers, right, on the ground, or in some scenarios that we consider, to airborne servers with more capabilities. So you see our testing field. It's actually a football field, so everything is line of sight. The UAV is flying around in a cylinder. There is nothing too extreme here. The motion is of this kind of quadcopters is fairly fast, actually, and erratic. But other than that, we are in line of sight. We are not in a busy street. So we were expecting, a nice degradation of a delay, some nice pattern when looking at the performance of these distributed pipelines. And this is instead what we got. So what you see here is, again, delay based on Wi-Fi connectivity to multiple edge servers at the same time. So this is the task level delay, so how long it takes to send the image, get back the outcome over time. And you see that the delay patterns, even in this simple environment, are extremely erratic, right? So we have a lot of peaks, a lot of sudden peaks. We don't have these nice degradations that we're expecting to observe. So this is not, a kind of signal that a pattern of delay that can support the control of a UAV, right? This is a problem, and all those delay peaks, all those things would degrade control eventually. So most of what we did in the end actually comes from the question, what can we do to stabilize this delay? And honestly, I can tell you that modeling, simulations are not going to show this kind of effect. A lot of what you see is based on, what you will see is based on experimentation and comes from the physics of the problem. But again, what can we do to stabilize this delay? And we reason at multiple levels. And I think that to really stabilize and provide this kind of services, you need to look at different aspects of the problem. So we work at the algorithm level, and the question is, can we design deep neural network that facilitate offloading? At the device level, we try to harness information that is observable by the device to make decisions about how information is processed. So do I analyze the data by myself? Do I send it to the edge? What servers? So that device level decision making, essentially. And then there is a whole system level, where the infrastructure is trying to decide how much resource to allocate, how to accumulate information to control this kind of system, and that's also very important. So I'm going to show you some pieces of this solution. So at the algorithm level, I'm going to show you a design called split deep neural networks, where we essentially modify the architecture of deep neural network to have a compression point and facilitate the transfer of the data, essentially. At device level, I'm going to show you a deep reinforcement learning agent that we train, essentially to dynamically decide where to process information based on information that is accessible from the UAV. And then we are actually currently working at the whole system perspective. We are now looking at network slicing, AI-based network slicing and hierarchical learning federated learning for this kind of problem. All the results are preliminary, so I'm not gonna talk about that. I'm gonna focus on the first two blocks. So before we go into those blocks, I'm just gonna, as I promised, I'm gonna briefly mention what we are doing in terms of healthcare. So we have this line of inquiry, which is essentially trying to develop a system to improve the well-being of pregnant women in underserved communities. And the whole logic is about integrating in-home visitations with fine-grained monitoring in everyday settings. So the idea is to use, I'm going to show the system, wearable sensors, so smartwatch, smart rings, essentially, and also information from the smartphone to detect stress, to make recommendations that are going to help the person to, for instance, reduce stress on average. So we developed this kind of multi-tiered system where you have wearable sensor, edge computing, cloud computing. And the main technical challenge here is that this kind of interaction with the person is not very easy. So detecting stress in everyday setting is extremely challenging and the whole classifier essentially needs to be personalized to the person, to the specific person. And the problem then is how I'm going to collect the data to personalize the detector. And for that, we are developing, and now we are testing in clinical trials, an interface which is implementing an active learning agent that is controlling how we ask the user to label data so that we get samples essentially from the sensor so that we get meaningful labels without bothering the user too much. That's a very important problem. So we developed this whole system and we are now starting to test. Some of the problems are still very much connected to what I'm gonna talk about today. For instance, if you want to detect stress, you need the morphology of physiological signals. That's a lot of data. So some of the split computing, split DNN ideas that I'm going to show you also play a role here. There's also the problem of reliability, of resource optimization. That's also very important and connected to what we did. And of course, please feel free to ask me more questions about this. Again, we are in the process of testing in a real deployment some of our logics. So going back to our main problem here, I'm going to start with the device level problem. Okay, so how can we make the system aware of what's happening at different layers and decide where to compute, essentially, where to execute deep neural network. Okay. So again, the main problem is that even in a relatively simple environment, we have extremely erratic pattern of delay. So what can you see that the baseline delay, the average delay is relatively good, but then we have all these spikes, right? So the kind of problem that we have in mind is a selection problem, right? For instance, if you take this from a more traditional communication perspective, you could think, okay, I implement some form of handover between the edge servers. So I try to use, for instance, the edge server with the best channel, right? So that's a sort of more traditional handover. Unfortunately, this seems to be not very effective. And for instance, if you look at the center plot, so we have the delay, the distribution of the average and variance of delay as a function of link quality. And you see that there is not a lot of correlation. And this is very surprising because we were expecting to see a very clear connection between link quality and delay. So which means that the system is a little more complex than we thought. And the rightmost plot is, again, delay, average, and variance as a function of the distance from the edge. So you could say I'm gonna essentially have some form of geographical based handover. Also, in that case, there is not much correlation between distance and delay distribution, which means that the problem, again, is complex, right? And I can give you an example of this. For instance, quadcopters are extremely dynamic, right? And when they accelerate, they tilt. When they tilt, essentially the physical layer at a very fine grain, so you can think of channel estimation, is disrupted for a little while. You lose a section, maybe a 1 or 2 packets, maybe. And that creates a cascade effect over the whole stack. So, you can think of access, transport layer, and eventually application layer queuing, right? So there is this sort of interaction between the physics of the device and the whole stack at a very fine grain, temporal scale, longer horizon as well. So all these complex interactions are extremely difficult to model, and there is no one feature that is going to tell you, there is going to be a peak in delay. You need to look at the system as a whole. So there is weak dependency if you look at specific features, while you need to really understand the pattern that the system is taking. And my point is that to do so, you need to look not only at the application layer, at the network layer, but also at the device itself, at telemetry, right? So this is our logic. The idea that we have is that we're going to use essentially a dynamic form of task allocation within the system. So the UAV, again, is generating this stream of tasks, and we have a smart agent, in this case, that is a deep reinforcement learning agent, that is deciding to which servers, so how many and which servers we send the task. So this is a form of controlled dynamic task replication strategy, which is based on the uncertainty, essentially. So if you, if you are very much sure that one edge server is gonna give you the performance that you want, then you can bet only on that server and send the task only to that server. If you have uncertainty because you think that peak may come or may not, right, on different channels and servers, you may want to spread your task to multiple servers and essentially increase diversity. The problem is that that's using more resources. So if everybody is doing this all the time, like sending tasks to multiple servers, then the system's load is going to increase. So we need to trade off, smartly, the amount of resources that we use and the performance of the system. Formally, again, what we're trying to do is we're trying to minimize the average usage of servers and channels, essentially, under constraint on essentially the fraction of tasks that are executed, that are resolved with a certain delay, right? So we want the delay to be below a certain threshold. We want to constrain the number of tasks that exceed this delay threshold, because again, a delay that is larger than some threshold is going to harm control. So the problem is very simple. To do this, we built a very simple form of predictors, right? So we look at predicting the probability that the next task over one server will have the delay above or below the threshold. We also develop predictions logics that look at larger horizon in time. So looking at how many tasks are going to be executed within the delay constraint. This predictor takes the form of very simple deep neural network, but this kind of logic is a myopic logic, right? We try to predict the delay, the next task, and then we act on it. The other solution that we developed is based on deep reinforcement learning. So I'm not going to talk much about this. I guess most of you know about deep reinforcement learning, but the whole idea is that we are using we change the reward function, right? So we train the system to optimize the behavior over a window of time, and so this adds some capability actually that is very important, as demonstrated in the results that I'm going to show you in 1 minute. So all of this is experimental, right? All these effects come from experimentation, and one of my students actually spent quite some time in building what we call the Hydra middleware, which is this software, open source software actually that we released, that is essentially an AI-based multiplexer, which is routing tasks to dynamically to different servers, edge servers, based on the decision of a deep reinforcement learning agent. And you see that the system itself is actually logging features from network, from telemetry, and from application layer. So we log what's happening in the system, and we try to make decisions based on what we see. Okay, so the logic is very simple. doing it in practice and connecting it to the flight control of a vehicle took a little bit of time, but I think it was worth it actually. And this is, some details in the implementation of a deep reinforcement learning agent that we develop. We use a specific kind of deep reinforcement learning strategy to, again, base on a block of features that you see in the matrix. So we take all the features in a window of time. Now the problem is that that's a lot of information, and if you were to train and so to design and train a deep reinforcement learning agent based on all those features, then the model itself would be fairly large. And what we're trying to avoid is actually executing large models, right? So the first thing that we did is actually use an iterative strategy an iterative algorithm to identify what are the most informative features, to reduce the number of features that we use. So you see in that table that we have some examples of features that we use. So some come from the network, like round trip time, transmission timeout, channel level. But you see that there are features that actually come from telemetry, which is inclination. Well, we have altitude, but also heading and speed. And heading was actually, relatively interesting because, of course, heading is going to tell you where the drone is going, right? So in which direction. So that, there is a clear relationship between the position of a drone and heading. But heading also has a relatively strong impact on short-term prediction, and that's because the heading is going to tell you the orientation of a drone with respect to the edge server. And again, in our drones have legs, and legs actually are body obstructions essentially that also have an impact on the quality of a link and on the dynamics of a link. So again, the problem is interesting as you need to use features from all the blocks. So and you see this here. So this is essentially area under the curve, which is a metric that measures the accuracy of the predictors that we train as a function of a time interval. So how long is our prediction window? And you see this is a function of different feature blocks, and the higher the better, right? So if you only use telemetry, you see that you don't have a good prediction in the short term, but you have a good prediction in the long term. And this is because telemetry is going to tell you, essentially, it's going to give you some longer term effect, essentially. So I tilt now, and something is going to happen at the network, and it takes some time for things to happen, right? If you look at network features, which is the blue line, and you see that network is going to tell you as a high predictive power in the short term, but then cannot really predict delays in the long term because network is very volatile. So there is not a lot of correlation. And if you use application layer features only, which is the green line, essentially the delay itself, then the delay has low self-correlation, so that's not a very good prediction feature, essentially. So you see the red line, if you use the features that I show you from all the blocks, you have good prediction performance in the short term, in the long term, and this is very important for the deep reinforcement learning agent to work properly. So there's another interesting thing here to consider, and is that we are not using all the channels and edge servers all the time, right? Sometimes we are not transmitting the task, we're not transmitting anything essentially over some of the channels, right? So in that case, we lose most of the network feature block, right? So you're not transmitting, so you don't get a lot of information about what's happening over the channel. You still get some of it based on the link essentially that is kept alive. So you get channel quality, you get some like the beacons essentially, but you don't get a lot of information. And this has an impact. You see that in the graph. So where I'm plotting the same thing that I showed you earlier, but you see that if we don't offload the task to one server for one task, we go from the blue to the orange. then to task, we go from the orange to the green, and so on and so forth, right? So what the message here is that if I don't use a channel/edge resource, I lose predictive power in the short term, which means that a myopic policy here may suffer, right? Because I may be confident in making decisions, but my information is outdated and my prediction accuracy may be degraded. So I actually don't know what's happening in the system. So the trick that the deep reinforcement learning agent is using, actually, you see this here, is actually optimizing the way we sample the channels to maximize prediction power in the future as well. So this is, the final plot of this block. Essentially, if you use just a best channel quality to control task by task, by the way, which server you use, you get in this setting, you get 75% of the task below a certain delay. If you use our predictive logic and you see the leftmost point of the blue line, so you use one server, but with a predictive logic, so the predictors that I showed you earlier, you get 85%. And then the more resources you use, the higher the performance, right? The higher the number of tasks that are executed below the desired threshold. Now, the problem is that, again, a myopic strategy based on one-shot prediction may lose prediction power, right? So you see when a small number of resources are used. So you see the deep reinforcement learning agent there, which is the orange line, essentially has a much higher performance when we use a small number of servers. That's because the deep reinforcement learning agent is essentially acquiring information not only to offload, but also to control how much information we have for future decisions. So that's also very interesting to me. So you see here a very simple example. I have a video. I'm not going to show you the video because sometimes when I do that, I lose audio on Zoom. But we have a real-world demo with the UAV flying around ground and airborne servers, and we are expanding the data set to essentially include lidar-based navigation and also more advanced communication interfaces like Mat-User MIMO, more like millimeter wave. And so we are now in the process of collecting data set for that as well. So this is one important point. We are also doing some more work in terms of connecting what the vehicle is doing to offloading. This is a paper that, again, in the work, but we are essentially trying to connect the state of a controller to decisions in terms of whether to process locally or at the edge server based on characteristics of the processing itself. So you can think of, again, local computing on board the UAV having essentially a deterministic small delay if we use a very simple but inaccurate model, while edge computing, we have a lot more uncertainty. We have possibly a longer delay because we are transmitting information, but we can execute effectively larger models, right? And this has an impact on control. So this is actually a plot that comes from the UAV trying to follow a target. And you see the tracking error with edge computing and local computing. At time 10 seconds, we have a discontinuity in terms of the velocity of the target, and so we change direction and speed of the target, and you see that local computing and edge computing, the ranking changes, right? Sometimes local computing is the winning strategy, sometimes edge computing is the winning strategy. So this is still in the works, but we are trying to connect, to make these decisions based on what's happening in the system. And that's also very important from the point of view of resource usage, because if a UAV is in a very simple environment, then it doesn't make sense to use large models and that consume a lot of resource in terms of server and channel, right? And energy at the UAV as well. So I think this is interesting direction as well, which we are exploring right now. So here I have some papers that we published in this on this topic. Again, we're still working on many of this, and we're expanding the test, but I think there's a lot to do in terms of this kind of cross-layer, cross-component logics, dynamic control of the dynamic computing control logic. Now, what I show you, right, is assuming that computing tasks are monolithic, right? So we either execute the model at the UAV, and maybe we need to execute a smaller model, compressed model, or we execute the whole model at the edge, right? But in that case, we need to send the data to the edge, and that's the bottleneck here. There is an intermediate option that came out maybe 4 years ago, 3 years ago, which is called split deep neural networks. And the first papers actually were proposing a very simple way of doing this. So you take the model, you cut it to create 2 different sections. One section called head model is executed at the mobile device. The second section called tail model is essentially executed at the edge server. And in this case, you are transmitting, rather than the input, you are transmitting the output of an intermediate layer, right? There is a famous paper on this called Neurosurgeon, but actually it's showing that it's very funny, actually. It's showing that this approach doesn't work. So in most applications, and the reason is very clear, actually. So if you cut the network, and you allocate a portion of it to the mobile device, you're executing the network, like a portion of a network in a weaker device. So it takes a little longer time compared to edge server. And then you are transmitting data, right? The output of a layer over the network. And the problem is that a lot of networks that are relevant to this kind of application, for instance, like computer vision networks, like the early layers are convolutional networks that actually amplify information. So they are not looking for correlation among pixels, right? And so you're actually, if you cut the network early, you are transmitting more data. So there is no advantage of that. If you cut the network later on, where you have maybe more compression, right? You can think of a deep neural network as a compressor, essentially, from the input to the output. Then you are executing a lot of the model at the mobile device, and that makes the system not very accurate. Of course, there are more refined techniques that came out in the last few years. And if you're interested in this topic, we recently published on Computing Surveys a survey on split computing and early exit in the context of mobile computing. So the problem, again, you see here the blue line. So this is essentially the size of a tensor with respect to the input, compressed input, which is the green line, over the layers. And the blue line are some existing models for image classification. And you see that to achieve a decent compression level, right? So 1/8 of the input size, you need to go very far away, actually, in the layers, which means we are allocating a lot of computing to the UAV, essentially. So this kind of brutal approach of just cutting the network is not feasible in this kind of models. There is no early natural compression point, if you want, in the model. So what we proposed in our papers is a different approach. So we take the model and we modify the architecture. So what we do essentially is to create a compression point that we call the bottleneck by downsizing some of the layers to create this kind of encoder-decoder structure. Now, the idea is that you split at this bottleneck layer, and in some recent papers, we actually use little more refined compression techniques. We use entropy coding. We use, more advanced, essentially, variational autoencoder techniques. But the key here is that within the network itself, you are creating this in-model compression point, right? And so you may ask, why don't you just use an autoencoder, right? So an autoencoder would take the input, compress the image, then you have decoder at the other side, which is decompressing the image, and then you run the model. So the problem of that is that, first of all, you will need to execute the autoencoder, which again is an additional burden to the system. And the other problem is that an autoencoder is essentially designed to reconstruct the input, right? Which means that you are taking the image and transmitting a compressed form of the image, reconstructing the full image at the other end, and you are using complexity and your bits essentially to represent portions of the image that you don't care about, right? You can think of an object with a lot of background. You don't care about the background. You care only about the object. And a standard autoencoder would essentially try to capture all the details of the image. What we're doing here is different, because by creating this kind of bottlenecks and training the network as a whole, we are training the encoder-decoder structures that are embedded in the network to encode information that is relevant to the task. And I'm going to show you an example of this. So you can look at this as a form of supervised compressor, if you want, which is a lot more effective than an unsupervised compression approach, which is, again, not doing what the model is supposed to do, which is transforming the input into the output, right? So in the interest of time, I'm going to go a little fast here. So we have many different approaches and many different bottlenecks and training strategies. But you see here the orange curve is, again, the size with respect to like the number of layers. So we were designing bottlenecks that would, compress, quite a bit in the early layers, right? So we created these bottleneck structures. In our more recent papers, we actually compressed up to essentially 2% of a compressed image, the JPEG image. So you are transmitting 2% of the data, and we are doing this very early in the network, right? And which means that we are allocating minimal computing to the mobile device. And you can do this. I mean, the problem then is this going to work, right? Are you going to degrade accuracy a lot by having this kind of compression? And the answer is that if you just use a standard training approach, then you are aggressive in the compression and size of a head model, essentially, then the degradation is fairly high, right? So to preserve accuracy, we devised a different training approach, which is a multi-stage training approach based on knowledge distillation. So what happens is we freeze portions of a model and train the rest. So in the first stage, we freeze what is the second part of the tail, and we just train using knowledge distillation the encoder-decoder structure. And this actually is training that portion of a network to have very effective compression and representation, latent representation, essentially. When we freeze that part of the network and we refine the last part of the network, which is taking that representation and transforming it into the final output. And this actually improves a lot the performance. We also applied this to a slightly more complex way of doing this kind of compression, again, using entropy coding. And that actually has very good performance, and we are compressing essentially by up to 2%.
Yes. 1 minute.
Sorry? Okay. So just to show you, some experimental results very quickly, we tested this on different configurations. So using NVIDIA Jetson Nano, Raspberry Pi as mobile devices, a stronger laptop as edge server. We tested this on Wi-Fi, LoRa, and LTE. And very, very briefly, so this is energy consumption, which is a very important, the distribution, of power consumption, actually. So if you use local computing, you see on the right you have a lot of power consumption, essentially up to 6 watts, actually. If you use smaller models, you have a more deterministic power consumption, which is the blue line there. And our split logics, are much on the left toward deterministic, almost deterministic power consumption of 2 watts, which is very close to what pure edge computing is achieving, which means that we are executing very, very tiny models at the mobile device. If you look at the delay, of course, whether or not this strategy is gives you a lot of advantage is a function of channel quality. So here you see an example on LTE channel quality. So of course, if the channel quality is bad enough, the delay decreases a lot. You see from 0.3 to below 0.1, and this is the total delay. If the channel quality is a lot better than edge computing, it might still be a comparable option, but you see that we have actually still a good gain. And local computing is actually takes a lot more time if you run this kind of model. In smaller systems, you have also like a Raspberry Pi, you still have a very high energy consumption if you execute this model locally. And if we use our splitting models, you have a 9.2% increase in terms of power consumption with respect to pure edge computing. Okay, so a much smaller increase in power consumption. We also tested this again on LoRa and smaller devices. Again, whether or not the advantage of this kind of technique or how you compute is really a function of the configuration of the system. So how powerful the mobile device is, how powerful the edge is, how powerful how good the channel is, of course. So different configurations are going to give you different average performance. But of course, in this kind of setting, it's also very important to make this whole thing dynamic, which is the connection with the first part of the talk that I show you. So we are working at making this kind of logics more dynamic, and we have some recent results on this as well. So just to show you what supervised compression means. Here you see on the right the bit allocation of our model with respect to actually very strong variational autoencoder. And where you see red, it means that our autoencoder is essentially focusing the representation, is allocating more bits. And you see that we are focusing on the objects and we are disregarding the background, essentially, which is what we expected in essence. So these are, again, we have a lot of results. This is getting quite some attention, and it's becoming a trend in our research community. If you're interested, we have a survey. I'm also happy, of course, to interact further. And well, I'm gonna skip this. I have another approach, which is also like a cute approach, but given that I'm running out of time, I will just go to the last slide and just hope that I was able to convey that this kind of problem, right, needs to look at across different components of a pipeline. You need to look at the algorithm, you need to look at the channel, of course, the communication technology, but also at the decision making of where you compute. And this kind of systems are extremely dynamic, are extremely difficult, and unfortunately are also extremely demanding. Right? So it's not an easy problem, and we are putting together pieces to solve the whole problem, which is of course not very easy. So please ask any questions.
Thank you very much, Marco. Thank you for the talk.